right, cool. Okay, so name the following compounds based on what we discussed last class. All right, our first introduction into organic chemistry nomenclature. All right, so what was step one? What do we got to do first? Count carbons, but specifically in the, somebody said, the parent chain. Yeah, the longest chain that you can find, right? So counting carbons, but specifically the longest continuous set of carbons that we can find in that molecule. So 1, 2, 3, 4. Okay, so that means my parent chain is a, what is the 4-carbon prefix? Butane, right? So the weird ones are the first 4: meth, eth, prop, and bute. And after that, it kind of just goes with what we learned in geometry class, right? Pent, hex, hept, oct. But the first 4 are the ones that I would like spend a little bit more mental energy remembering because they are just kind of out of left field, okay? 4 carbons is bute, so butane. Again, the whole logic is we got to count for all the carbons in this compound, so I still got to account for this one here. This would be what's called a methyl group, because it's just got that 1 carbon associated with it. And I got to indicate the position of that methyl group, right? So we can always number our parent chain 2 ways. 1, 2, 3, 4. 1, 2, 3, 4. And the numbering scheme I'm going to pick is the one that gives that methyl group the lowest possible number. So red or purple? Purple. All right, so to finish this off, this would be 2-methyl butane. Okay, and I got these 3 components of my name, just like I've color-coded here, although the methyl's a little messy. You guys get the idea? All one word, right? Ram it all together. But 2, that's the location. Methyl, that's the substituent. And then butane, that's my parent chain. Okay? For this one, the only tricky bit is when we're finding our parent chain, we got to remember that it's not just from left to right, but the longest continuous set of carbons that I can find. So it's really tempting to say 1, 2, 3, 4, 5, 6, but I can get a longer one if I start here. 1, 2, 3, 4, 5, 6, 7. And so since that's the longest continuous set of carbons, that's my parent chain. Okay? So 7 is the prefix hept. So my parent chain here is a heptane. I still gotta account for these carbons. So this is a 1-carbon group. This is a 2-carbon group. So this would be a methyl group. And this would be an ethyl group. I'm again, I'm going to number my parent chain. 2, 3. 1, 2, 3, 4, 5, 6, 7. So purple is 2 and a 7. Red was a 4 and a 6, right? So then it's going to be my purple numbering scheme. Shucks, yeah, 2 and 4, my bad. That makes way more sense. 2 and 4, and the other one is 4 and 6, right? So I'm going to go with that purple numbering scheme because it has the lower number in there, okay? And then when we assemble our name, what order are we going to put it in? Alphabetical, right? So when I'm numbering, I'm just going to pay attention to the lowest possible number, but when I assemble my name, I'm going to put it in alphabetical order. So 2, Ethel.
No, it's 4.
Jesus Christ. All right. I'm paying attention, I swear. All right. 4, Ethel. Seeing if I can stump you all. It's all on purpose. 4, Ethel. 2, methyl heptane. Again, ran together, all one word. All right, again, I have the numbers indicating the location. Any sort of substituents, anything off of that main chain, I have labeled in my name as well, and then the actual parent chain. Okay, so this was our introduction to alkanes. Thus far was just naming them. Pretty much every functional group that we get introduced to, that's going to be step 1, is figuring out how to name those particular compounds, right? Again, the nice thing is that as of right now, all these rules are brand new, so it's going to seem like this very pain in the butt process. We're just going to apply that same set of rules over and over again for every new functional group that we learn. Okay, so today we're going to switch gears and we're going to talk about reactions of alkanes. Okay? And alkanes, like I said, they're kind of a boring functional group. They're not all that terribly reactive. There's really only 2 reactions of alkanes that we're going to cover, one of which you're already probably familiar with, and these are combustion reactions. All right, and then the other one, which we're going to talk a little bit more in depth about, is what's called radical halogenation. Okay, but let's first spend some time talking about combustion. It's pretty straightforward. A combustion reaction would be, for example, a formula like C4H10, that's my alkane, plus O2. Does anybody remember the products of a combustion reaction? They're always the same 2 products. CO2 and H2O. All right, and all of these are gases. This, it depends on your fuel. I think butane is a liquid. Okay, but they're all going to have this exact same chemical formula where you have some alkane. In this case, I chose C4H10, but it could be anything, right? Any number of carbons reacting with O2 to produce CO2 and H2O. Always those same products, right? So the only thing that could ever change is the identity of your alkane. Okay? A combustion reaction is the reaction that's powering most vehicles, or at least unless you have an electric car. A combustion engine operates on this reaction right here. Many sort of fuel sources, whether it be coal or natural gas or gasoline, you're still basically doing the exact same thing, where you're taking some sort of a hydrocarbon, some sort of an alkane, reacting it with oxygen to produce CO2 and H2O. This reaction right here is what's responsible for all that excess CO2 that we have in the environment. And why is that? Because this reaction releases a crap ton of energy. In terms of like the amount of fuel that you have to have versus the amount of energy that's released. It's just more effective than just about any other chemical reaction that has been discovered up until this point. Not to mention the fact that like these alkanes, these hydrocarbons, are fairly readily available down underneath the soil of the earth, right? So we have these sort of massive oil reserves. So the two of those factors combined is why humanity has taken such advantage of this particular chemical reaction, right? Huge energy payoff and relatively easy availability of the fuel source of those hydrocarbons, okay? So we can just note, huge amount of energy released. Right? I mean, which is why even to this day, even with all modern technology, we're still having a heck of a time trying to phase out this particular reaction, right? Just because the benefit, the payoff is so large. There's obviously a downside too, which we've come to reckon with, but nonetheless. All right, so what do we need to be able to do? Importantly, if I give you any fuel, you should be able to give me this chemical equation, because again, it's always just with oxygen producing CO2 and H2O, right? And then the other thing that we need to be able to do is just going back to general chemistry, we should be able to balance this chemical equation. Okay, so everybody take a second and take a stab at balancing this chemical equation, and then we'll work through it together. All right? Remember what the heck I mean by balancing this chemical equation. That's what I want you to try to reach back in your brain and do. So what do I mean by balance? What are we trying to achieve here? I know you all know what balancing a chemical equation is. What are we trying to do when we balance a chemical equation? To have the same number of carbons on both sides, the same number of hydrogens on both sides, and the same number of oxygens on both sides, right? That's the name of the game, okay? For a combustion reaction, there's kind of a strategy that's going to make our lives a little bit easier, and that's to save the oxygens until the end. If you try to do the oxygens first, it's much more of a pain in the butt because it's in both of these compounds here. So anytime you adjust one of them, it's going to change the total number of oxygens, right? So our strategy is going to be to save oxygens for last, all right? Meaning we're going to focus first on the carbons. And what's going to make this easy is that all of the carbon from that hydrocarbon just wound up in this carbon dioxide, right? It's not in multiple places, it's just in that one place on either side. So that's what makes balancing carbons first easy. How am I going to balance my carbons? What am I going to do? I'll put a 4 out front here. Hydrogens, same story. It's easy because all of the hydrogens over here end up in this one compound over here. It's not all over the place, okay? So how am I going to balance my hydrogens? What am I going to put out front here? 5. A 5, okay. So now that I've balanced my carbons and hydrogens, now I can go back and worry about the oxygens. So again, focus on carbons and hydrogens first. Let's just make a note. Focus on C and H first. Now I can go back and total up how many oxygens I have, right? So on this side over here, I have 8 from the carbon dioxide and 5 from the water, bringing me a total of 13. Okay? Is there any number that I can put out front here that would make this 13? Why, what's the problem?
Uneven.
Can't use decimals, 13 is an odd number, and this is necessarily like in order of 2, right? So that's not gonna work out for me. We could, if it was allowed, do something like 13 over 2, but again, fractions aren't allowed, okay? But if we can get to this point where it's balanced, it's very easy to turn these all into whole numbers, to get rid of that fraction, okay? So, we can say if O2 is balanced with a fraction, we're just going to multiply everything by 2. All right, so again, this chemical equation right here is balanced. You can convince yourself that you have the same number of carbons, hydrogens, and oxygens on this side as you do on this side. The only problem is that it's illegal to have a fraction here, but it is balanced, okay? So we can correct that very easily by taking this whole thing, this entire chemical equation, and multiplying each one of these coefficients by 2, okay? Every single one of those coefficients is going to get hit. So this becomes now, let me just copy to save myself some time. Let me make more room so this is not too terribly ugly. I don't know what that is. Okay, I'm going to replace all of these coefficients by doubling them. So now this is a 2. What's 13 halves times 2?
13.
Just 13. A nice, neat whole number, right? So that's why I multiplied by 2, so I could cancel out that fraction. 4 multiplied by 2 becomes 8, and then 5 multiplied by 2 becomes 10. And now I have a nice, balanced chemical equation where all of my coefficients are integers, right? So I'm good. Okay, so this first reaction, combustion, again, you should be able to draw me or given any sort of an alkane, you need to be able to give me the balanced chemical equation for the combustion of that alkane. All right, radical halogenation. What the heck do we think halogenation means?
What's the state that we're putting next to the C4H10?
In this case, you'd have to be told what it is because they're all different.
Oh.
Butane's actually a liquid, but propane's a gas, and then some of the big, so you'd have to be told that. You don't know what that is right off the bat. You do know that oxygen's a gas, carbon dioxide's a gas, and actually the water that's produced in these reactions, because they're so high energy, is water vapor, not liquid water. Okay, so you do know these 3 states, but for the fuel itself, you have to be told what that is. All right, good question. All right, so again, halogenation. What do we think a halogenation reaction is going to do? What familiar word do we spy there? Halogen, right? So this is where we're going to take our alkane. We're going to use a simple methane at this point just to illustrate this reaction. We're going to react it with a halogen, so it's either going to be chlorine or bromine. Okay, so I'll do my example with chlorine here, but we are going to just make a note that it could also be bromine. All right, and you do this reaction in the presence of light. And so how we represent light in a chemical reaction is this H fancy V, H nu. It has to do with physics, all right? But anyways, that just represents light. Okay, and what we're going to see is that now we have stuck a halogen onto our alkane. We also get HCl. What we're going to see over and over again in organic chemistry is usually we're really only focused on the organic product of a reaction. Balanced chemical equations are absolutely necessary for doing things like stoichiometry, but again, there's not really a huge math component of this course, so really it's going to be about what happens to that organic structure. So what's going to be even more important than this balanced chemical equation is sort of being able to draw your structure and being able to see how your organic molecule is being transformed. In this case, I'm swapping out or substituting a hydrogen for a chlorine. That's what's happening in this reaction. Okay? So being able to draw products of our reactions are going to be the main focus of the study of these reactions. Okay, and so this is our second functional group that we've been introduced to. This is an alkane, and this is what we call an alkyl halide. We're going to talk a lot about alkyl halides. They're fantastic starting points for reactions. They tend to be very highly reactive, so they're great starting points. In this particular case, it's actually the end point, but yes, we're going to see them quite often. All right. So first of all, said radical halogenation. We covered the halogenation portion, right? Because that's what you're doing. You're sticking a halogen on there. So what the heck is radical? It does not just mean that it's an extreme. A radical is an actual thing in chemistry. Okay, so what is a radical? A radical is any atom with an unpaired electron. All right, so what do I mean by that? If we have chlorine and it's got 4 lone pairs, that means it's got a negative charge. This is just a chloride ion. All right, where it's got 4 lone pairs. But if one of those lone pairs isn't a pair, it's just one electron all by itself. So for example, this, that now has this one unpaired electron here, this would be a chlorine radical. All right, and whereas paired electrons, and in this case this chloride ion, is fairly stable, especially because it's a chlorine and it likes being an ion, this is highly reactive. All right, these unpaired electrons are pissed off. They are trying to react with anything and everything in sight because electrons like to be paired, right? So the fact that this is this unpaired electron, we're going to see kicks off this whole series of reactions here. Yeah, it's just a highly reactive species. Okay? So our radical halogenation reaction has, all radical reactions have 3 steps. The first step is what we call initiation. This is the formation of the first radical. Okay. So we take our chlorine gas, our diatomic chlorine, right? This is just Cl2. I've just drawn out the Lewis structure for it. Okay. Make this bond a little bit bigger. And what happens is, then we're going to hit it with that light, and it's a fairly high energy photon that we're going to use. All right, and what we're going to see is that this is what creates our chlorine radical here. Okay, what happens is the light causes this bond to break in such a way where one electron jumps onto this chlorine and the other electron jumps onto this chlorine, okay? These are what are called these electron pushing arrows. Okay, and what we're doing is we're moving an electron from here, the base of the arrow, to here, the tip of the arrow. Right? So just what's being represented here is we're picking up one of these electrons and putting it onto this atom, picking up the other electron and putting it onto that atom. That's how we get our two chlorine radicals out of it. So that is the initiation step, the formation of that first radical. And it doesn't happen to every single one of those chlorines in solution, but it doesn't have to. Even if it's 0.0000001% of those chlorines that form a radical, they're so highly reactive that that would kick off this series of events and we'd have a full set of reaction on our hands. So even though only a tiny population is ever in that radical form, that's all you need in order to propagate these reactions. Okay, because they get involved in the next step, which is the propagation step. And in the propagation step, we'll see radicals creating more radicals. And our product is formed in this step as well. Okay, so in the first step, we have our radical. So we can say step one. A radical is going to steal a hydrogen from our hydrocarbon, from our alkane. Okay, and so this will create HCl. And now a carbon radical. Okay, and this is going to be the feature that we're going to see over and over again in these propagation steps. You got a radical on one side and a radical on the other side, right? Propagation, it's going to continue going here. Oh, okay, thank you. yeah, we got a radical on one side and a radical on the other side, okay? So step one, the radical steals a hydrogen, so what happens is this angry electron reaches out and grabs this hydrogen, and that causes this bond to break in that same way we saw up here. All right, and now in step two, the carbon radical reacts with a second chlorine molecule. So now we again have our diatomic chlorine, and the radical is going to do what the radicals do, which is be angry and grab other atoms. So what we get on the other side is now our new chlorine-carbon bond, right? We get our halogenated product. Okay? And what's my other product of this reaction? So we got, what do we have on this side that's missing from that side? That second Cl. Okay? And in particular, because this is that propagation step, I'm going to have a radical on one side and a radical on the other side. I've just reformed that same chlorine radical that I started with, right? So notice how the first step I started with the chlorine radical, that's what's kicked everything off. At the end of that propagation step, I also have a chlorine radical, right? That's why it's called the propagation step, because now this guy is just going to go and react with another molecule, and that'll create another chlorine radical that then reacts with another molecule, and that will just keep on going and going and going, okay? So at the end of these two steps, I get just what I started with again, which is why it's called the propagation step, because now this can just go back and start the whole thing over again.
So from step 1 to 2, how did we get the second Cl?
Because this is now a new Cl2 molecule that's floating around in solution, right?
Okay.
There's not just one of them, there's a ton of them, and only a teeny tiny fraction was ever converted to radical in the first place. So most of the chlorine that's floating around is still just Cl2, right? That's why there's a ton of that ready to go to react to form these radicals here. That is definitely one of the more confusing aspects of like pencil and paper chemistry, is just keeping in mind that we don't just have one chlorine molecule, right? We have an entire beaker full of these molecules that are reacting with one another. Okay, let me make more room here. Okay, and then the last step is sort of what finishes it all off, what's called the termination step. And this is when two radicals find one another. And what's going to happen when two radicals react with one another is they just now form a non-radical, right? A normal molecule. So what would that look like? Okay, in the rare event that we have these two chlorine radicals finding one another, so here's one, here's another. Both of these chlorine radicals have these unpaired electrons, right? So they're both angry. Well, they can just very easily join teams and form a paired electron, right? So this one will say, all right, let's contribute mine, you contribute yours, and now we've just reformed a normal old covalent bond. And so as the name implies, this will terminate that reaction, right? Now I've stopped being a radical. I've stopped this sort of propagation step because two radicals have found one another. Okay, and it could also be, or that we have our carbon radical finding a chlorine radical. This would also do it. What's up?
So in terms of radicals, it'll either propagate or terminate?
Yes. So once they're formed, they're going to propagate, and they're going to propagate, and they're going to propagate until the rare chance that two of them find one another, then it's done. Okay, so these are our 3 steps of our radical reaction. The initiation, the creation of that first radical, the propagation, which is where we actually get our product, our alkyl halide, right? And then finally, the end, when 2 radicals find one another, the reaction will finally yield. Okay, so this is like all the information that you could ever display about these particular reactions here summed up in these diagrams. But now we have a sort of natural question here, which is, I started out with methane. There's only that one possible product that we can get, right? But what happens if I start out with something like propane? If I do the same thing, okay, and now I'm going to get lazy in true organic chemistry form, and I'm only going to pay attention to the organic product. HCl is always formed as well. We don't care about it. Doesn't matter. All right, that's not what's important. We care about what's happening to those carbons, right? What happens to the organic molecule. And we got 2 different possibilities, because I can have my chlorine sticking onto one of those end carbons, or I can have my chlorine on that middle one. All right, so we got 2 possible products. Which is the major product? Okay, we're going to lay some groundwork here, but by the end, that's what we're going to be able to answer about this particular reaction. Out of these 2 products here, which one's going to be the major product of this reaction? Okay, so before we can address that, we got to first talk about the stability of alkyl radicals. And this is why we bothered learning that primary versus secondary versus tertiary designation for exactly these kind of situations here. Because it turns out that the stability of an alkyl radical depends on that level of substitution of a carbon. A tertiary alkyl radical is the most stable, followed by a secondary alkyl radical, and then a primary alkyl radical. Okay, so if I ask for the most stable radical intermediate reacting this particular hydrocarbon here, which carbon am I going to put that dot on? Carbon 1, 2, or 3? Which one is going to be the most stable alkyl radical here? So first of all, let's color code here. Do I have any primary carbons in this molecule? Which ones? 1 and 3 are both primary. And what about a secondary carbon? Do I have any of those here? That'd be this one here. Do I have any tertiary in this molecule? No. So the most stable intermediate would be when that dot, that radical, is on that middle carbon, the secondary carbon. Right? The more highly substituted a carbon is, the more stable that radical is. Okay, so I'm going to put down some examples, and you guys are going to draw me the most stable radical intermediate for these particular hydrocarbons. Really trying to break it. Okay, so again, if I'm going to just go through and identify primary, secondary, and tertiary carbons in each of these molecules, this one has these 2 primary carbons and these 2 secondary carbons. And again, the more stable intermediate is going to be, radical intermediate is going to be the more highly substituted. So I can put the dot there. Do I need to include them both? Why wouldn't I have to include them both? They're the same, exactly, right? If I picked this thing up and flipped it over, I would just have that exact same molecule. So I'm not going to include them both because I've just drawn the exact same thing twice. What's up?
So it wouldn't matter which for this one we
Nope. Yep, it wouldn't matter which one you chose because they're identical structures. Okay, which I know is hard to see at first, and that's something that we're going to have to get good at, but yes, these are exactly the same thing. So we wouldn't include them both we would just include one, but either or would work. Okay, so then in this one, I have these 3 primaries. I have this secondary, but I also have this tertiary carbon right here. And so my radical is going to form on that tertiary carbon, that more substituted carbon. Okay, so now for this one's a little bit tricky because it's very tempting to say that my radical should form on this one right here, because this is the most substituted carbon. Anybody identify what the problem with that is? It's already got 4, right? And let's just remember how these radicals are formed. I have to be able to pull off a hydrogen. That's how I formed the radical to begin with. So those quaternary carbons, they don't have any hydrogens that you can pluck off. So they can't form any sort of radicals at all. So it's not going to be here on my quaternary carbon. It's going to go on the next most highly substituted carbon, which is that secondary one there. Right? So if I just follow my color coding here, I got these 1, 2, 3, 4 primaries. I got a secondary and no tertiary. And again, we're not going to count that quaternary because there are no hydrogens. Cool. All right, so this was step 1 in terms of figuring out what our major product is, and we'll finish this off next class with how we figure that out.